Hello and welcome. Contour integration, lecture number 3. The real integral sine to the power of 6 times the cos to the power of 6 integrated between 0 and 2 pi. This particular integral can be done many different ways. You can do it by setting up a reduction formula. I think maybe even you can transform into a beta function if you change this limit into a pi over 2. I can't quite think at the moment if I can do that as it is. What else can we do? We can actually even use normal complex numbers from A level, but I'm going to do it with contour integration today. So this is what we're going to do. This is of the form some kind of function of sine theta and cos theta with limits 0 to 2 pi. So for something like this, we're going to use, of course, a unit circle centered at the origin as the contour. Okay, so let's draw that first of all. So that's my gamma, my contour, radius 1, so this is the point 1, 0, and this is real z and im z. So the next thing that I need to, it'll be traced of course in an anti-clockwise direction, and the next thing is to transform this real integrand into some complex function f of z to be integrated of course over this particular unit circle. Okay, what's the parameterization that we ought to use for something like this? Is quite clearly z is equal to e to the I theta from 0 to 2 pi. Let's get our dz, and our dz is going to be I e to the I theta d theta, which we can write as Iz d theta, and we will be after the d theta there, so d theta is going to be dz over Iz. So we're going to, of course, integrate around gamma, and we need to change, of course, the sine to the 6 of theta times the cos to the 6 of theta. I could do an in-between step. I can actually change that to the sine of 2 theta to the power of 6, but probably I will leave it like this as it is in there. So, of course, we ought to know these facts about the sine and the cos. This is the sine that I'm writing in here. So this is 1 over 2i e to the I theta minus e to the minus I theta. So that's a sine of theta times, this is the cos, a half, e to the I theta plus e to the minus I theta. That merely says that's the sine of I theta, and this says the cos of I theta. So this is sine times cos, and of course it needs to be to the power of 6, and the d theta we did change, and the d theta turned out to be dz over Iz. So of course the next step is quite clear. We need to move all these exponentials into z, given the fact that z is e to the I theta. So a couple of tidies. Let's write this 1 over 2 times 2 is 4, 4i to the power of 6. I'm going to pull it outside this bracket, and these two brackets still inside the big square bracket to be powered to the 6 is going to be z minus 1 over z, because of course e to the minus I theta will be 1 over, and the other one's of course exactly the same but with the plus, and still all to the power of 6, and we got extra bits here, the Iz. Okay. Next line, shall I evaluate that 1 to the power, sorry, 1 over 4 to the power of 6, or shall I just leave it like that? 4 to the power of 5, I know it's 1024, or 2 to the 10. So an extra times 4, it will double it, so it's 2048, 4096. So this bit here, I'm going to pull it outside the integral. It's going to be equal to 1 over 4096. What's going to happen to the I at the bottom when it gets power to the 6? The power of 4, it leaves it invariant, and then I got a nice squared, which will switch me to a minus 1. So that is just this bit here. evaluated. But of course, I've got a 1 over I from this bit here. So let's put the I there so we account for all the bits and pieces. And inside the integral now, I will have the difference of squares. So z squared minus 1 over z squared, all to the power of 6 times a 1 over z dz. Okay, so far so good. Looks a little bit messy, very big numbers in there. Is it difficult to do? Well, this is the complex function f of z, and I need to find its poles and then its residues. This is a mess. I'm not going to be doing that in the usual way that I've been doing many other integrals before. This, if I can expand it, I got powers of z, and if you go back to lecture number 1, I did actually show that all powers of z, when integrated around a circle like this, for example, they will have 0 contribution except the 1 over z term. And the 1 over z term, I don't know, before I even do it, you can actually see when I multiply this bracket out, okay, I'm going to get a term which is independent of z here, and then the times 1 over z, I only need that particular term in order to just answer my problem. Unfortunately, my brain is at the moment is not working very well, so I'm going to have to do a full expansion. I do apologize rather than make a mistake. It will be also useful for you to see what I was referring to, because some of us cannot actually see what's going on a little bit. And if you go back to lecture number 1, revision of complex integration, this will make more sense again now. So let's write this line. I'm writing it above. Let me just take the other line off as well, so we have some gap underneath it. Okay, so this is equal to minus 1 over 4096 I. And this expansion now, I'm going to write the 1 over z first. That's this bit here. And this binomial expansion is not that difficult to do. To the power of 6, the coefficients are 1, 6, 15, 20, and then go back down. So they're going to be z to the 12. Terms will alternate. 6 z to the power, it'll be going down in 4s. Then it's going to be a 15. Z to the power of 4, then a minus, there's the 20, no z on this term, plus 15 again, over z to the 4, then a minus 6 over z to the 8, and then we got the plus 1 over z to the 12, close bracket, dz. So this is just this bit here. And I'm going to save myself a line and multiply this 1 over z. So what will happen in there, all the powers will change. So if I times by 1 over z, I'll write the 1 over z afterwards. This becomes z to the 11, z to the 7, z cubed. Now this is the key and important one, which I'm going to take the red pen to write it. That is going to be 20 over z. And then the other powers will change to z to the 5 here, z to the 9, and z to the 13. And of course the 1 over z will disappear from the front. I multiplied it out just now. So this is now what we got. And you can see I'm not going to use the residue theorem directly by saying, okay, let's work out poles, let's work out residues of poles. I have already my integrand written as a series, so I can actually see what this particular contour integral will actually give me. Remember on lecture number 1, we did actually prove that all integer powers of z, when integrated around a unit circle, a closed curve, which contains the origin, all of these things have 0 contribution. They will integrate to 0 except one very special term. That is the 1 over z term. The integral, I'm writing it here as a reminder, of 1 over z dz is going to be 2 pi I. So in order to actually see better what is going on in there, I'm going to factorize out the minus 20, the coefficient of that, pull it outside. By the way, this is the residue. if I was using the residue theorem properly, the residue is by definition the coefficient of 1 over z. So the residue, it would have been a simple pole at the origin with residue minus 20. I'm going to move this minus 20 on the outside, so it's going to become a plus now, 20 over 4096. And this integral now, I can throw all these bits away. It's going to be, of course, the integral of 1 over z dz, which of course this is going to be 2 pi I lost the I there, I do beg your pardon. Okay, so the answer to the real integral that I was trying to find is 20 over 4096 I times 2 pi I, and thankfully, because of course the integral is real, we cannot get possibly a complex answer out of this. The i's cancel, and what does that simplify? We got 40 pi over 4096. As per usual, I didn't check the answer. We can cancel that down. We can keep halving. There's 2, there's an 8 in there. 5 pi, 4096, 2048, 1024, 512. So I'll make this integral 5 pi over 512, and of course this integral is the same as, of course, whatever transformed into the complex plane, and this is the answer to the real integral that I was trying to find. I hope you followed it. A little bit different to the usual stuff that I've done recently. Who's laughing now?